So when we first learned how to find the distance of a line segment, so let me suppose I just had something that looks like this. So if I, back in the day when you were starting off in your math career and you were asked to find the distance of this line segment without you using a ruler, well, what did we do? Back in our early algebra days, I should specify. Well, what we did is we figured out the length of our horizontal value, right? We said, okay, what is our x and what is our y? And we really just established, we used the Pythagorean theorem. We said x squared plus y squared is equal to, and let's just call this distance right here r. Okay, and we said this was equal to r squared. And then how do we find the value of r? Well, we say r then has to be equal to the square root of our horizontal component squared plus our vertical component squared, right? The theorem that we're just using is the Pythagorean theorem, and the formula that was often given is just the distance formula. Well, that was great. But what about if you were then given something that looked like this? And that's not a very good curve right here. So let me just kind of fix that. If you were given like a curve like this, and then I asked you to find the length of this curve, well, in this particular situation, you trying to kind of approximate this, I mean, I guess you could kind of like maybe draw a line here and get an approximation, but clearly they're not going to be the same. So what do we do? Well, we're pretty far along in our calculus career now, and we kind of know the sense, we get the sense here that what we probably want to do is find out what happens over a small portion of this curve, and then see if we can come up with a generalization. In other words, if I were to just go ahead and start by just finding a very, very small line segment, right? I know I'm even making it larger than it actually would be. But if I found the length of a really small line segment, I could technically try to find the length of this small line segment by looking at a really, really small x and a really, really small y and applying the distance formula or the Pythagorean theorem to that small portion. And then I could rinse and repeat. I could then look at the next very small line segment and then again apply the distance formula to something like that. And then repeat this. And then just go ahead and find all of these little line segments, find those distances, and then add them up to get a really, really good approximation for what's happening here. Now, if only we had something in calculus that adds up an infinite number of really small partition values, whether they're area or lengths. And your inner calculus student should be screaming out integration. And that's exactly what's happening here. So we can really just continue our understanding of what's going on with the distance formula and integration to find the length of a given arc. And so there are different variations of this formula depending on whether or not you're looking at a polar function or a parametric function or a rectangular function. But for parametric vectors, or excuse me, parametric equations or for vectors, the idea is effectively the same. For each one of these really small triangles, what we're doing is we're saying for a very small change in x and a very small change in y, we can effectively just treat those as really small partitions here, and we're just going to apply the distance formula or the Pythagorean theorem here. That's all that's happening here. And we're going to integrate, meaning we're going to add up all of those distance over the interval from A to B. So let's go ahead and let's try a very quick example of this. So for this arc length here, we could use our calculator if we want to here. I'm not going to really go into this too much because I think just the understanding of where this formula comes from and kind of why it makes sense is probably the most important part of this lesson. But let's find the arc length here of this plane curve given by these two parametric equations from the interval from 1 to 3. So the interval is from 1 to 3. So first off, let's say dx then is just equal to, or dx dt, excuse me, is equal to 2. dy dt would then be equal to negative 5 over t squared. So to find the length here, let's set this up. It's going to be the integral from, our interval is from 1 to 3, the square root of, and that's a terrible square root, I'm going to do that again, the square root of dx dt, which is going to be 2 squared, because we're squaring, plus dy dt, which is negative 5 over t squared squared with respect to t. That is going to give us our arc length. Now, for the sake of time, I'm just going to let you kind of punch that into your calculator. And in fact, you should get a little bit more comfortable putting this stuff into your calculator. But clearly you see there that that is something that you could do by hand. But let's just go ahead and punch that in, and you should get approximately 5.434. So that's the length of this arc using the arc length formula. Okay, let's try a couple of more examples. Let's look at this problem now here below, number 4, that I have written on the back side of our notes. Use the arc length to show that the unit circle, x is equal to cosine t, y equals sine t. Again, these are just two parametric equations that give me the unit circle. If you were to graph those, it gives you a plane curve that creates the unit circle, a circle with a radius of 1. So we're just going to use the arc length integral or the arc length formula just to show that that unit circle does indeed have a circumference of 2 pi. We know it does, right? But we're just going to use calculus to kind of confirm that for ourselves. Well, what is our arc length going to look like? So our arc length is going to be the following. Our integral, we're going to be integrating from 0 to 2 pi. And I'm choosing 0 to 2 pi because that's the normal interval for t given when we're graphing the unit circle. And we're going to write the square root of the derivative of x here. So dx dt, maybe I'll just write that here. Dx dt is what? Is equal to negative sine t. And dy dt is equal to, what is that? Cosine of t. All right. So we're going to say dx dt, so negative sine t squared, plus dy dt, which is cosine of t squared, all of this with respect to t. Now, before you go ahead and punch that into your calculator, just look carefully at what's going on right here. We've got the integral from 0 to 2 pi. Well, what is negative sine t? Well, that's sine squared t, or sine t squared, plus cosine squared t. Does that look familiar to you? And yes, that is a Pythagorean identity. All of this we know is equal to 1. So you're just integrating 1 with respect to t. And what is that? And that's just going to be equal to t, and we evaluate it from 0 to 2 pi. So what you just are going to get 2 pi minus 0, which is just 2 pi. And that's sort of neat. All right. Okay. This next example, we are going to be integrating using our calculator, but those of you who are feeling up to it, I highly challenge you to, or not highly challenge, I encourage you to see if you can try to do this next problem completely by hand. Hint, you are going to want to use the half angle formulas, but for our intents and purposes, let's go ahead and just use a calculator to actually integrate here. But let's make sure we have a setup, and that's going to be a common thread throughout these problems. I want to make sure you know how to set this up first by hand, and then from there we can go ahead and use our calculator to evaluate some integrals. So let's find the arc length here. I'm going to switch colors just to help you kind of organize this. Let's determine the length of the curve to find from that x and y equation. Well, so first off, let's find dx dt. So dx dt is the following. It's going to be the derivative of theta minus sine theta is 1 minus cosine theta. And dy dt is going to be, let's see, what do we have there? That's just sine theta. So our length, pause the video right now and see if you can set it up on your own before you write it out. It's the integral from 0 to 2 pi. We have dx dt, so 1 minus cosine theta squared plus sine squared theta, d theta. This time our parameter is theta, okay? And then from here, we can actually just put that into our calculator. Again, if you can do it by hand, awesome. But what you should find once you do all that is your arc length is equal to 8. Okay? All right, now the last problem that I want to talk about, number 6, is actually another pretty heavy calculator problem, but go ahead and punch those two parametric functions into your calculator. Make sure you switch into parametric mode. And if you do so, then you should get a graph, and I'm just going to roughly sketch it here because I can't show you what I have on my calculator just now. But it's going to look something like this. This is not a great graph, but just trying to do a rough sketch here. So you should get a graph that kind of looks like this. It should look like almost like a pouch. Some people have said bomb or some other things. But In order for me to set this up, the immediate question that a lot of students have is, what are my bounds of integration? You didn't give me an integral, or an interval here, I should say. And I'm asking to find the length of the loop here that's created. So this parametric function is going to start from this direction, and it's going to move kind of counterclockwise. And then it's going to loop all the way around. So this is the direction. These are the directional arrows of our plane curve. And then it's going to continue going on in that direction after that. So it's going to loop counterclockwise and move that way. What we want to know is, where does this loop begin and end? Where is the t-value here? Where does it start and where does it end? Now, you could go ahead and use your calculator for this. You could just go ahead and use your calculator and try to use the trace feature and approximate that as best as you can. You're going to get some decimal values, and it's because it's actually an irrational number. It's a radical value. Now ask yourself, is there a way that I could have done this without having to rely on my calculator? Well, pause this video and think about that for a moment. And what you should find here is that, yes, this coordinate here that I have kind of highlighted, this coordinate is actually 0, 9. So you could go ahead and plug any one of those x and y values back into your original parametric equations and find your t values for which that works, right? Let's say, for example, I just set my y value 9 and set it equal to my parametric equation. So y is equal to 3t squared is equal to 3, so t is equal to plus or minus root 3. So what we're saying here is that when t is equal to negative root 3, that's where this starts. This is actually a t is equal to negative root 3. And it's going to loop back around, and when t hits positive root 3, it's going to close that loop. So now we know where our integrals begin and end. So we can say negative root 3, positive root 3. And then from there, we can just go ahead and write the square root of what is dx dt. Well, that's the derivative of our x equation. So that's just going to be 3 minus 3t squared, all of that squared, plus the derivative of 3t squared, which is just 6t. We're going to square that, do this with respect to t. And if you integrate this by hand, the nice part about that is you will get an exact value. Turns out this is 12 root 3. If you punch that into your calculator, you should see that it's approximately 20.785. All right. So the big thing is really making sure that we know how to set up these integrals, and then also making sure that we're increasingly comfortable with how the parametric curves work, so that we know where we're going to be starting our integration and where the upper limit is going to be.